Cool. So thank you to all my teams for the great neuroscience background. It's a lot of neuroscience, so let's break things down a little bit. So we know that neuronal activations entail thoughts and ideas, right? And then, so if we analyze these activations, can we talk about thoughts by analyzing activations? So that's one of the key things to keep in mind. And then this is back in the pitch. We say that if we can create this gadget or this gear, then can we get some causal relationship saying that the activation of LC system we created links to internal representations or conditions? Keep in mind that this is a very big claim, and we make maybe a little small step towards it. And then so we propose that if we can actually make the system first and then record activations from this system by fitting to a neuroscience data set, can we get some trigger of psychological phenomenon, for instance, rumination that we care about? And then how would they be represented in the internal states of the network? So this is what we care about. So this is back in the previous pitch. I'll just go over really quick. Basically, the recipe for computational models is data-driven. There is some sort of model that we use, and here's a neural network, and then we have this gadget here that's try to pretty much imitate the LC system, and then we fit to a neuroscience data set, the behavioral data set that Ivy was describing earlier. Cool. So the data set, just give everyone a quick overview. The left corner is basically the distribution of pupil dilation. And you can see that I wouldn't call this like super separable. If you see, this is the difference between arousal and neutral. It's saying basically, is the participants getting the condition to be stressed or not? And then, yeah, so I would even say that it's pretty magnificent that our model even distinguishes between them at all. And the correlation matrix, I would say probably duration is the highest correlative factor to talk about this. But all of this is from like sort of a mathematical and computation perspective. But what do we care in neuroscience is a lot more. So just on planing, we drop pretty much half of the data because there is null data. We can't use null data. And then we eventually pick these features to fit our model. And the key thing is that the full data set consists of 9 participants, and then it's a lot of roles, right? You see there at the beginning there's 3,000 roles. So it's temporal information for 9 participants across the experiments. And this is just a view of how it actually looks like. Cool. So what can we do with the models, right? So a bunch of things. We did some traditional neural network model, a cortex fitter model, which essentially we tried to build in the whole LC idea into neural network directly. That didn't work, by the way. The thing that actually worked was the neural gadget, which the difference between the second and third is that the third is sort of a neural network playing around with the LC system. So, and then it's an uncertainty model. It incorporates some sense of memory, and then it incorporates modulation because it's the self-learning gadget. So, simplifying it, we have a neural network. We have this controller, some sort of memory, and then pupil dilation with uncertainty as prediction. So this is fitting to the data set. And this is how our full model actually looks like. And then incorporating to each section, so it looks like this. And then here is just some mathematical formulation. I'm not gonna go over at all. This is more for discussion later if anyone are interested. Just key insights is that we pick some very specific choices of activation functions to essentially model neuroscience effects the best. 10H has a range of negatives to positives, which meaning that it can have gains or losses in modulation both, comparing to like just ReLU with positive values. So the architecture, again, this is just a breakdown for later if I need to come back. And then the loss function is essentially we try to incorporate certain uncertainty measures into the system. And then, okay, so we fit for the models. We did string test split. Usual traditional models didn't fit pretty well, I'll say, but it's very aggressive. And then the cortex fitter is very careful in fitting. But then this is what we have for our model. And I'll say it's not bad, considering that the data set itself is actually not that easy to deal with. And this is uncertainty, and I just make this line to show that what a perfect prediction will be like. So it's off by a little bit, but it's something. Cool. So that was a lot of jargon. And so we have this model, right? So what really is cool about it is we can do, remember the previous picture and all the neuroscience background, we can do activation analysis on it. So that's what we care about. So comparing with the original study that Ivy was talking about earlier, we basically have the idea that if LC is activated, right, it strengthens thread-related memory, it causes rumination. So we will see different representations, which is also part of our analysis. So some intuition, does our model even make sense? One sad news is that we failed to create the inverted U-curve directly out of it, and we suspect that it's probably because we don't have a spike model in the phasic and tonic control, which is also some improvement we need to do. Currently, the two phasic and tonic is essentially two other wave matrices that's getting modulated. And then, but we do see some, intuitively it sort of makes sense that, less LC activation seem to be dealing with low dilation, low uncertainty conditions, sort of fits the idea we have been keep seeing in neuroscience literature. So yeah, so just reality check wise, that sounds making sense to me. But what we really care about again is this mid layer of representation differences. So let's make a huge assumption. Let's say that rumination is about stuck in certain modes of firing in the activation, meaning that you are having this recursive thoughts, keeping your mind that it's stuck there. So neuronal wise, it's this stuck in certain modes of activation. So naive thoughts, we do some cosine similarity graphs on the activation space with this 96% is actually handpicked. And then so basically we can see that under stressful conditions, sort of all the activations are clustered much more together comparing to neutral conditions, which gives us an intuition that maybe that there are some certain differences and then stressful conditions maybe do have different activations patterns. But then that's not enough, right? Graphs are just graphs. Can we do some quantification of the graph and then can we capture some temporal information with it? So again, naive thoughts, this is a statistical tool called pretty much autocorrelation function. We try to see one variable is corresponding to the future version of itself. And then we see that, under stressful conditions, they slightly have a little bit higher autocorrelation. So the activation seems to be a little bit more prolonged. But then I don't think that's enough. So traditionally we do PCA. This is also what we did in the pitch, but we're not doing that here. We want to do something else that's a little bit funner, probably digging a big hole here, but we're going to do topological data analysis. And then, so just a quick background, so it actually all makes sense later on. Doing topological data analysis, we're trying to, so think about every single activation, it's a vector in space. And then we try to form connections between them by this process called filtration. So we try to make this spherical objects growing around each data point, and then they connect each other in the end. And then this is what makes this sort of spheres. So you can see in this process. And then the key thing is that these connections are called connected components, and then they would start to make a spherical objects like the cycles above. And these cycles dies because once connection grows, these sort of triangle in the middle may be connected together, and then they will enclose the circles. So this represents this sort of higher dimension cyclic structures, deaths and births. And this happens to be quite critical later on in our analysis. And then just a quick thing, these H0 essentially represent connected component. H1 is the cycles that you have seen. And then the dashed line is essentially saying they get born and then die at the same time. So it is a null effect. Cool. So what does that have to do anything with neuroscience? So previously, people have done a lot actually with topological data analysis, and then they've found that these sort of higher dimension structures seems to be correlated with certain psychological ideas we talked about. For instance, people have found that higher order interactions like the loops indicates that there's higher correlations with attention. And then other studies have also done pretty much, it's sort of a showcase of that it's being used in neuroscience. And the key takeaway is that it seems like attention is related to higher level components. And then maybe we can say that rumination is a showcase of overactivation of attentive to previous thoughts. So we're trying to sort of connecting the bridge between what we're doing and then what we try to do and then what's currently happening in neuroscience. So then can we say that these sort of connected components represent thoughts, and then we see that there is short-lived components, that means that it's highly flexible, and can we say that these H1s are cycles in the activations, they are the recursive thoughts, and then if we see many persistent loop, then we're saying that it's recursive thinking. This is a big assumption, which probably not very accurate, but it's for like a course project, we think it's a good step. And then, so basically this is the same thing. We think that if it quickly disappears, it's flexible. If it persists, it's sort of more of a rumination sauce. So key thing, long lifetime for H0 and then longer lifetime for H1 is an indication of stressful condition in our experiments. And we will see that results will show us something. So this is the persistent homology graph that you guys see earlier, which is actually coming from our real data. And then we see that they're actually somewhat a little bit far from the diagonal line, showing that there are components that's been forming in the activation space. And we want to look at them separately, right? We want to reason about different conditions between neutral and stress. And we see that somewhat like the black sort of framed points, which is the stressful ones, seem to have higher magnitude here, showing that there might be more these sort of cyclic components formed in stressful conditions. But yeah, cool. That is basically graphs. Can we do more quantification again? So we can do some certain statistic distance tests. We measure how different they're away from each other, and then we can do pretty much hypothesis testing. We show that the p-values are significant, and then we reason about from the local and individual level. Then we can talk about more from a distribution level. We do the KS test. This slide is also for reference for later. And then basically the key idea here is we try to measure the distance between the cumulative density functions between all the lifetime of each components. And then we see that, again, the key thing is we do see that there is a significance p-value, meaning that under stressful and neutral conditions, we see cyclic components having different lifetime, meaning that maybe there's rumination. And we see in the H0 place, we see that the mean lifetime for stressful conditions is a little bit longer. That may indicate that it's more persistence of ruminating thoughts. And we do care about the significance difference here. Cool. So the lifetime, a little bit more tests. We do non-parametric tests to see the distribution of birth and death directly. And we see that, again, there's a significance, specifically in death time, which is actually what we cares more a little bit here, because we're trying to talk about the durations of these components. Cool. So there is difference. So a lot of math, a lot of computer science stuff. Conclusion, there is difference, but can we say that there is some difference in directions? Because remember, back in the beginning, we say that maybe that's if we have longer H0 and H1, that indicates that it's rumination. So we do a few more topological analysis. One is seeing the global shape, and I actually want to, for the sake of time, I want to focus on this one more, which is the Betty curves, and this is actually also being used in previous neuroscience studies as well. So I want to talk a little bit about this. It's essentially that we see that the numbers of components being formed in this topological space. And we can see that for stressful conditions, we do have more of them. So this is sort of one key findings we sort of find is that seems like under stressful conditions, there are more connected components, higher level, specifically for cyclic cycles forming, that may indicate rumination. So what we have learned, again, we have delivered a neural gadget controller that sort of mimics the brain's idea using brain's mechanistic insights to fit neuroscience data set, and then trying to talk about rumination. And then we have this unique approach towards analyzing the representation of the model, trying to quantify psychological concept within these representations. And we have found that we've quantified these different representations, and the representations are indeed different between stressful and neutral conditions, and we can quantify them with statistical tools. So at last, just some improvements. We think that, of course, this study is for 10 weeks, so we don't really have times to ground it with neuronal actual data, like RSA comparisons, but for future references, maybe we'll do that. And also the drawbacks we have discussed earlier, that it's not a spiky model, so maybe that's why we didn't recreate the inverted U-curve, but more sophisticated models for the future. And yeah, this is basically it. We can take any questions. Thank you.
I mean, it was like very early on in the thing, but you showed training error on one of your models. Do you have like a test error graph anywhere, or is it like? Hold up.
I think it's very early at the beginning.
Yeah, I can
This one, right?
Yeah.
Yeah, so this is actually, this is not the training arrow, this is the test arrow directly. So it's
Left?
right.
Oh, okay.
Oh yeah, the loss curve is, sorry, yeah, the loss curve is for the training arrow, but yeah, I didn't graph for the loss curve for the test.
Uh-huh.
And then it's directly the predictions on the test sets.
Right. Oh, okay, cool. Yeah.
Questions?
Can you just go back to your diagram showing the description of the model?
This one?
Yeah, I just wanted to look at it for a second.
Oh, yeah.
This is not fast.
I know, everything went so quickly.
No, I created
No,
this.
this is the one with Craig.
Yeah.
So that was quite a tour de force. That was a lot, I mean, it was great. I needed longer though, but it was great. Thank you, nicely framed, and I like the motivation. It's so cool that you pulled an actual data set and did this. So when you went into topological space, which is hard actually. So are you thinking that the ruminations are reflecting back and forth between like different topological spaces? Is that what you're, I understood the analysis, but are you directly saying that that's what's happening with the rumination?
I guess
That
it's,
there's a mapping?
we can't say for sure, but it's sort of this intuitive understandings, because like when we, like, the idea of using topological analysis was actually developed, like, we were like, okay, what is rumination? It's recursive thoughts. What is recursive thought? It's like a thought that's going around in a cycle. So the first intuition was actually using PCA, and then we realized that PCA might be too simple to actually capture any nonlinear trends.
Yeah.
So then we were basically looking into more quantitative measures of how people have done this, and then it turns out that looking at cyclic components, especially because I've done previous cyclic components with gate cycle analysis, so I was like, okay, both are loops. So then can we say, but one is for behavior, one is for like psychological thoughts. So is there some similarities that we can draw from each other? So that's sort of where we get to the topological analysis.
Yeah, I mean, it makes good sense, actually, that the same sort of loops, just like in safety monitoring, you know, when our corticothalamic, basal ganglia corticothalamic loops, you know, if you think of that sort of cycle of rumination, you would expect the same sort of thing for action as you have for thought, which you can think of as internal action. So I really like that mapping, actually. I just wanted to know if that's it.
Yeah, thank you.
Very cool.
Because we do actually have, because the one of our limitations was that the data set was kind of small, especially we dropped half of it, and then the columns are kind of a little bit limited to fit to. It's sort of like really black box in the middle, sort of less like data driven controls there. So we tried to find different data sets, but didn't work out too well. So this is why we end up using this data sets. But if we do have like a more descriptive, I guess the word is, data set that we can use, and especially if we can build things, spiking models, then maybe we can have a better representation. So currently our models is not that mechanistic yet, because I think the phasic and tonic controls doesn't have their full characteristic as how they are represented in neuroscience literature yet, but I think it's a small step towards it.
Did you use delay embeddings for your TDA?
No, actually.
Okay.
It was directly persistent homology, if I remember it correct.
Yeah, and since the data set is not really fit, like the PCA result is not significant, that's why we changed to other method.
Yeah.
Yeah, the PCA, this is actually from the PCA. It's from one of our earlier models, but basically the PCA is just very linear in separating things. That's,
Well,
yeah.
that's what it does.
Yeah.
yeah.
Orthogonal. It's not bad though. When you get at least some differences coming out in some of the pieces. Any other questions?